Hello everyone, I'm Kazuma Kawai in Nagoya University. Today, I'll talk about computing LP1 leveling with combined parameters. This is the outline of my presentation. First, I'll explain the background of LP1 leveling. LP1 leveling is originally motivated by the frequency assignment for wireless devices. The objective of this problem is the minimization of used frequency range. Frequency assignment has to satisfy the following constraints so that devices can avoid interference. First, very close wireless devices A and B, B and C need to use sufficiently different frequencies. Second, not very but still close devices A and C need to use different frequencies. These kind of situations are represented by labeled graphs. The vertices correspond to devices, and the edges correspond to the relationships between devices that are very close together. The assignment of non-negative integers to each vertex corresponds to frequency assignment. I give an explanation by using a concrete example. Assign the non-negative integer to each vertex, but they have constraints. B and C violate distance 1 condition, so change C's level to 0. A and C violate distance 2 condition, so change C's level to 4. This leveling doesn't violate any constraint. But their range can be improved like this. This leveling is minimum, so this one is optimal leveling in this graph. The formal definition of an LP1 leveling is like this, and the KLP1 leveling is LP1 leveling whose range of the levels is from 0 to K. The LP1 leveling problem is the problem to ask the minimum range of levels K among all possible assignment. The minimum K is called LP1 leveling number, which is denoted by lambda P1. There are various settings for the LP1 leveling problem. The most generalized setting is LPQ leveling, and by the definition, LP0 is equivalent to the graph coloring, and L11 is equivalent to the graph coloring of square graphs. So L21 is often considered as an essential leveling problem setting. Hereafter, we will consider cases where Q equals 1 and P is 2 or more. Let me explain the previous work about LP1 leveling. First, LP1 leveling problem is NP-hard for any positive P, and it is NP-hard even for the following restricted graphs. But classes of path, tree, cycle, wheel, cograph, and outer planar can be solved in polynomial time. As we saw in the previous slide, the LP1 leveling problem is NP-hard on very restricted graphs. So in this work, we focus on fixed parameter tractable algorithms. Previous work showed that it is para-NP-hard for various parameters. NP-hard on the planar graph even if the maximum degree 3 and even if the maximum level number 4. In addition, NP-hard even with a tree width 2. On the other hand, the FPT algorithms for vertex cover and for neighborhood diversity are designed. Let me show our results. LP1 leveling is FPT when parameterized by click width plus maximum degree, and by twin cover plus maximum click size. In addition, there is fixed parameter P approximation algorithm for LP1 leveling with respect to twin cover. This figure shows the relationship between graph parameters and the parameterized complexity. In this figure, the connections between two parameters implies that upper is bounded by a function of the lower. The parameters inside of the blue boxes are our results. In this talk, I present only the case parameterized by twin cover plus maximum click size due to time limit. To explain our algorithm parameterized by twin cover, I first present an FPT algorithm parameterized by vertex cover, which is proposed by Fiala et al. A set of vertices W is called a vertex cover of G if every edge UV in E satisfies U in W or V in W. In other words, at least one of the endpoints on every edge must be included in W. If we are given the vertex cover W, the graph can be drawn like this. Each small v in V minus W is an independent and unconnected vertex. As seen later, twin cover is a reduced variant of vertex cover. To explain twin cover, let me explain the definition of twins. Two vertices U and V are called twins if U's neighbors are equal to V's neighbors. If twins U and V have edge UV, they are called true twins and the edge is called a twin edge. By using these, a twin cover of G is defined as follows. A set of vertices X is a twin cover of G if every edge UV in E satisfies either U in W or V in W, or UV are true twins. By the definition, clearly any vertex cover is a twin cover. And given a twin cover X, the graph can be decomposed into a twin cover W and a set of cliques like this. As the property of a twin cover, vertices in the same clique in V minus W have the common neighbors in the twin cover like this. Here, we denote by omega the maximum clique size of a graph. In this graph, omega is 7 and the corresponding clique is like this. And let T equal V minus W and omega prime be the largest clique size in T. The idea of our algorithm is based on the FPT algorithm parameterized by vertex cover. In the case of VC, the vertices in the independent set V minus W can be categorized with respect to the neighbors in the vertex cover, and the vertices in the vertex cover side are labeled in a fixed manner. Then, we can try all the possible placement of labels in the vertex cover, and for each partial labeling, we only have to consider the unlabeled vertices in the independent set. Once we fix a labeling on the vertex cover side, we can expect that it is easy to consider labeling on the independent set side, because they are not directly connected, but some of them are at distance 2 via vertices in the vertex cover side. We can concentrate on just the distance 2 condition, and the relations are characterized by neighbors on the vertex cover side. Here, the distance 2 condition is important. In the distance 2 condition, it is okay to use just different labels, so the label values are not so important. This means that the number of usable labels is essential, and it is a key that the vertex cover algorithm works well. Using this observation, we can check the feasibility of labelings by ILP. In the case of twin cover, independent cliques Z in V minus X can be categorized with respect to the neighbors in the twin cover like vertex cover, and the vertices in the twin cover side are labeled in a fixed manner as well as the vertex cover algorithm. In the vertex cover case, we can concentrate on the distance 2 condition, because these are not adjacent. In the twin cover case, we similarly consider the distance 2 condition for vertices in the cliques, but unlike the vertex cover case, we have to consider the distance 1 condition because the vertices in the clique are adjacent each other. So they should be labeled by P above labels. That is, the label values themselves may affect the procedure of the algorithm. This is a reason why we cannot extend the idea to the twin cover case directly. So we need some additional ideas. Considering this, I show that a similar algorithm could be designed. There is no exceptionally large independent clique. That is, I'll give an FPT with respect to twin cover plus omega. First, I'll introduce the FPT algorithm parameterized by vertex cover, and then I'll generalize it. As I explained before, a twin cover is a similar but different structure. Due to the difference, there's some difficulty to design an FPT algorithm by twin cover, which I'll explain next. By overcoming this difficulty, I'll design the FPT algorithm parameterized by twin cover. Okay, let me explain the FPT algorithm parameterized by vertex cover. The algorithm roughly consists of 3 steps. First, determine the label assignment to each vertex in the vertex cover W within the following range. Second, for each partial labeling, determine the label assignment to each vertex of I within the following range. Third, solve the assignment of the remaining labels to I by ILP. We need to prepare to solve the third step assignment. Let I1 to IS be the set of vertices having common neighbors in W. And let X0 to XT be the family of all possible set systems on I1 to IS, such that whenever two distinct ij and ij prime are in Xi, then neighbor ij cap neighbor ij prime equal empty set. I'll explain with a concrete example. In this example, vertices 1, 2, and 3 have common neighbors. So those vertices are classified into the same group of I. Similarly, 4 to 7, 8 to 10, 11, 12 to 14 are classified in the same group of I. Small I is classified by checking whether it is adjacent to each vertex in W. Two distinct ij and ij prime are in Xi, then neighbor ij cap neighbor ij prime equal empty set. So, for example, set I7, I12 is not included in X. For each Xi, we prepare a set Li of labels, which could be used for vertices in Ij in Xi. Note that L0, L1 to Ld must be disjoint each other. Let small xi be a variable representing the number of labels using Li in the desired labeling. For such labeling corresponds to the assignment as shown in this figure. At this time, small x3 equal 2. This is an explanation of preparation for the assignment to I. I'd like to explain the FPT algorithm for vertex cover. Determine the remaining label assignments by this formula. Find the label assignment to I by solving this formula. In the case of vertex cover, since I is independent set, the label's assignment to II need only be different. But in the case twin cover, since T is quickset, the labels assigned to Ti may need to be at least P apart. Let X be twin cover and T be V minus X. This is example for vertex cover when L3 equals 3, 4. It doesn't matter which vertex you assign the labels to. On the other hand, this is example for twin cover. There are cases that cannot be assigned. What kind of graph is there no unassignable case? The following lemma is introduced to consider such graphs. Graph G is defined by cliques C1 to CH. In the descending order of the sides and their common neighbors Y. If size of L is sum of Cj or more, sum of Cj is P times size of C1 or more hold. There exists an LP1 labeling of C1 to CH using only labels in L. Note that the labels in L are at least P apart from A1 to A size of Y. A1 to A size of Y are the labels assigned to Y. By repeatedly using the previous lemma, and reassigning the labels, we can derive the following lemma. Let X be a twin cover in G such that each Ti satisfies omega I is Ni over P or less. If G has a KLP1 labeling, then G also has a good KLP1 labeling for X. A KLP1 labeling is good for X if it uses only these labels for X. From this lemma, if omega is Ni over P or less holds for all Ti, the algorithm for vertex cover can be used. So we want to transform it into a twin cover that is omega I is Ni over P or less for all I. Actually, it's not so difficult. Because if omega I is more than Ni over P for any I, all we have to do is move Ti to X. Then become omega I is Ni over P or less for each I by such moving. The size of X after moving is at most Tc plus 2 to the Tc times P omega. At this time, the size of X after moving is X prime, and the size of X prime is Tc prime. By such movement, it can be transformed into a graph of omega I is Ni over P or less for all I. Since the algorithm for vertex cover is available for such graphs, the remaining label assignments can be determined by solving this formula. This is summary of algorithm flow. First, independent cliques partition into Ti. Second, move and modify so that omega I is Ni over P or less for all I. Third, label assignment to each vertex of X prime is decided. The label used in X prime can be limited to this range. Fourth, for such each assignment, assign these labels to L0 to LT. Fifth, determine the remaining label assignments by ILP. Therefore, computational complexity of this algorithm is order 4pTc prime to the Tc prime times 2 to the 2 to the Tc to the 4pTc prime times time to solve ILP. That is, the LP1 labeling problem is the FPT for twin cover plus omega. Finally, I'll talk about the summary and future work. For the LP1 labeling problem, we propose FPT algorithms parameterized by delta plus tree width and by twin cover plus omega, and fixed parameter B approximation algorithm parameterized by twin cover. So, a natural question is whether the LP1 labeling problem is FPT when parameterized by only twin cover. To my best of knowledge, no one knows even an XP algorithm when parameterized by only twin cover. So designing an XP algorithm is the first step. Thank you for your attention.